Today we're going to finish up the stoichiometry, but yesterday we did not talk about limiting reactants, and unfortunately we've already talked about limiting reactants, so that lecture is kind of old. But we're now doing limiting reactants with gases, which honestly shouldn't be anything new, hopefully, but I'll work out a few practice problems here. Just to refresh your memory. I do have a lot of information in the notes if you need to look over that again. And so let's just go right to page 19 at the bottom there. It looks like the space to do all the work is on the other side of the page.
Oh gosh, it really is.
And right small. All right.
No.
I love these packets. Number one, at the bottom of page 19. The question asks, what volume will water vapor form? What volume will water vapor form when 40 liters of hydrogen, 40 liters of hydrogen, 25 liters of oxygen?
Wait, where we is?
We're on the bottom of page 19. Okay. And so we're looking for the volume here. Okay. And it also says that the temperature and the pressure remain constant. So if the temperature and the pressure remain constant, what would be a good temperature and a good pressure to work a problem like this out at? At STP, good. Now, whenever you see something like that, automatically gravitate toward STP, just to make your life simple. Okay?
I like this problem.
I know, right? So, now, before we even start doing the 4 steps of stoichiometry, you have to look and see, is this a limiting reactant type problem? And how can you recognize or identify that?
Well, yes.
Why?
Because there's 2 informations.
Good, there's 2 amounts for, actually there's an amount for each of the reactants. So if I'm giving you, like yesterday I think I may have given you like a gram amount of this and I didn't say anything about the oxygen. Well, since we have amounts for each of these, we need to find out which one of these is going to run out first. Again, limiting reactants deal with the least amount or the one that runs out first. So, well, let's go through the 4 steps. Step 1, write a balanced equation. Is that balanced? No. So, put a 2 there and a 2 there. And then with limiting reactants, it doesn't matter. Pick one. Doesn't matter which one. Pick one. Hydrogen or oxygen?
Hydrogen.
Hydrogen? Okay. So what we're going to do is we're going to start with one of them and we're going to find out how much of the other one will be needed if we want to completely react with all the hydrogen. Okay, so since we're at STP, and if you need to use PV equals nRT, you can still do that, but I'm going to show you the conversions here where we have 1 mole equals 22.4 liters. Okay. That when we do limiting reactants, it's probably a good thing to know that conversion. So I'll put my 22.4 liters on the bottom, and this is for 1 mole of hydrogen, since that's the one we chose, and it doesn't matter which one you start with. And so that's step 2. Step 3, we want to get rid of the units of hydrogen, and we're going to compare it to the moles of the other reactant, in this case, oxygen. So what values go in front of these? 2 and 1, right? 1. Yeah, so we're not doing the product just yet. And then what we need to do is we need to find out how much oxygen we're actually going to use or consume. So we want to go back to the unit that the other thing is in. Sometimes it'll be the same unit, sometimes it might be grams or something else. It's not a problem. So we'll put 1 mole of oxygen on the bottom. What'll go on top here?
42.4 liters.
Perfect. Now, if we look at this, okay, the 22.4s will cancel out. So really it's 40 divided by 2, which is 20, right? So based on this, who is my limiting reactant? I want to see if you guys can remember this or how to determine who the limiting reactant is.
Oxygen, because it runs out there.
Okay, does everybody agree with that? I'm not saying she's right or wrong.
Sure.
Sure? All right, so here's what you have to say to yourself. If I'm going to use all 40 liters of the hydrogen, I will need at least 20 liters of oxygen. How much do I have? Okay, so I'm going to use all of this, and I'm only going to use this. So I'm going to have 5 liters left over, right?
So the 40 is the limiting reactant.
Very good. Okay, so that's my LR. I've got one of them set up in there, 40 megas. And you can pick whichever one you want to work with. You'll need a calculator though. Good luck. So our limiting reactant is the hydrogen. Because I will only use 20 liters of the oxygen, and I have 25. Does that make sense, Beth?
Yeah.
Okay. So I'm going to have leftover oxygen. So now that I know who my limiting reactant is, I want to disregard or ignore.
What's that one called then? No.
This one?
Yeah.
That's the excess. So if, and I'll never ask you to determine who the excess is, but it's nice to know. Okay, so that's the limiting reactant. The hydrogen will run out
Well, that
first.
makes more sense because if it's, you have more of it, then you would have an excess, so that makes the other one.
Yeah, I like how
reactant.
that is.
Okay, that's
Yeah.
fine. The bad news is we'll always ask for limiting reactants, but it's nice to know who the excess is as well.
No, I know. It's
Okay.
just easier to figure it out.
Oh, sure, sure.
Yeah, figure out which one's which.
Yeah.
Okay. So now that we know who the limiting reactant is, now we can answer the question. So we'll start off again with the 40 liters of our hydrogen. We'll do the similar step here where we'll convert the moles of hydrogen, I'm sorry, the liters of hydrogen. Because if I say that oxygen is my limiting reactant, then I will produce too much water. In other words, once the hydrogen runs out, we're done making water.
So, why does it have to do with the next little,
Oh, this one's actually answering the question.
yeah, so why do we have to do that? Like the top one? The
We need to know
Why
which
do we have
one.
to do, I don't get where we have to do the top part to the bottom part.
Okay.
Like, what's that have to do with the bottom?
This tells us which amount we're going to use to find this.
So which amount you're gonna put right there?
Correct.
Okay, got it. Thanks.
Perfect.
Where the tissues at?
So once we've converted our liters into moles, then we'll use the mole ratio. So moles of hydrogen to moles of water. And what values go there? 2 and 2 from the balanced equation. And then we need to go to our volume unit, which is liters. So we'll move our unit moles of water down. Oops, not water, sorry. Yeah, that's right. And we'll put our 22.4 on top. Now, Jeremiah was upset because the answer is the same as the thing that we started with. Nothing wrong with that. That's good. Because the 2's cancel, right? The 22.4's cancel. So it's just 40.
That's really annoying.
So why
Why
is
do
it
we-
gonna be like that every
Once
time?
again, why do we have to do this?
This was an easy example.
Is that always gonna be the same?
No, it will not always be the same.
Okay, you attitude.
Okay.
No, it just so happens to be that because we started with the volume and we finished with the volume. Now,
So
generally,
volume now in here.
it might be a volume and I might ask for a pressure or a temperature or a mass amount or something
Well,
else.
you don't have any practice problems like that, so can we
Well,
just
be
use
patient,
this?
be patient. It's coming. It's coming. We've got more than just that.
Well, then we should do one of.
Hold on, look at this. We got more practice problems. You just can't see them yet.
Really?
In other words, don't get angry at a question like that. This is easy points. I know it's easy. That's good.
So you just take whatever your limiting reaction is, and then you look at the moles of like 2 to 2, or if it was 1 to 2, then you just multiply it by 2 and you get 18.
Okay. Here's what the question is. Hang on. Shh. Here's what the question is, and this is my interpretation of what you're asking. Just look at this and then multiply it times the mole ratio.
Yeah, because it's 20.20.
That's a check. You'll definitely want to show the steps. Okay. Always show the steps involved with the reaction. You want all the points possible. So that's a check. As you're working this out, you should say to yourself, well, I have a 2 to 2 ratio. It's at STP because all gases at the same temperature and pressure behave in the same way. So it'll have the same volumes And so that makes it really nice that, yeah, they should be the same. That's not a point to get angry and go, I just wasted my time. No, you just acquired a lot of points. This would be probably about a 10-point question. And that's easy 10 points, right?
No.
Okay. All right. So part of the homework, what is that, the 6s? Okay. All right, at the bottom of page 21, this is more limiting reactant type problems, more of the fun stuff actually. And this one's actually broken down so that you can put part of the work in there. All right, when potassium chlorate, KClO3, decomposes, how many grams, ooh, here we go, how many grams of KClO3 are needed to produce 30 liters of oxygen? 30 liters of oxygen at STP. Also, KCl is produced. Well, I'm kind of bummed by this. This isn't a limiting reactant problem at all, is it? How do you know that's not a limiting reactant problem? It only has one reactant, so that is the limiting reactant. Okay. Why, Maddie? There's only one reactant, correct? No, if there's only one reactant, there's only one thing on the left side, that is the limiting reactant.
It's on the right side.
No, it's on the left side. These are products.
Oh my god.
That's a reactant. All right, so step 1, is this balanced?
No, I'm already like way past you. Right?
Woo! No, it's not. So we're gonna need, go ahead, what? 2, 3, 2. Nice.
You're so Madeline.
All right, so it's balanced.
Madeline Sue.
So start with what you know. And how would I do this?
22.4.
If you choose to, or you could use PV equals nRT, but
The other one is so much easier.
I know, right?
I like this way because it's cycle and then
And then moles of oxygen, and we're going to moles of potassium chlorate, or KCl3. And what are my numbers there?
3.
2 and 3, okay.
Okay. I did.
So that's step 3, this is step 2. Step 1, write about the equation. What do we need to change this to? Grams, good. I think that's what you said. So potassium 39.1 plus chlorine 35.
122.55.
What?
Like all together, correct?
Oh, what was it again?
122.55. I'm hoping. 'Cause
I'll trust you.
Apparently, I'm not very good at math.
Should I trust her?
Can you check just in case?
Okay. So 109. Anybody get that? Good, bad?
Yeah, that was good.
All right.
How's it going?
In the notes on page 23, it says diffusion and effusion. Okay. I like to put these two together, kind of generalize them. I like to think of this as how quickly gases move throughout a space. In other words, if I were to bring in a big bottle of cheap perfume, no, even worse.
That's what Maddie wears.
Oh.
Even worse, bring in a can of Axe.
Ooh, that's what he
Because my 6th grade son has like 5,000 of these. His mother keeps buying them, and I'm like, stop.
I
Yeah,
don't
it's-
wear that.
Okay. Now, if I were to bring that can up and start spraying the Axe, okay, who would probably smell it first?
Those people.
Other than me. Those people, don't categorize it as those people.
It's not-
I don't know if I like it or if it's like my
Now, does everybody think that the gases kind of like move out like a wave?
Yeah.
Actually, no, Because what happens is, as a gas particle, there's already gas particles in the air. So even though Stephanie and Emma are close, they may not be the first one to smell it. It actually might be Zach or Vanessa on the other side, on the sides of the room, that might smell it first. Because when a gas particle hits another gas particle, it bounces. So it won't necessarily move out like a wave. Okay? That's what effusion and diffusion are about.
Would it be the same if I like farted?
Well, where you're at, possibly. Hopefully Maddie would be the first one to receive that, and not, say, maybe Heidi.
That's
Okay?
weird.
Big old gas bubble.
Yeah, and actually Heidi may smell it before Beth smells it, which is not necessarily a good thing.
Yeah, there are sometimes, like, if you're in a car and someone did it,
Yeah.
Oh yeah,
and you don't smell it yet. Like, sometimes everybody else
It-
has, but you don't yet.
That's
exactly.
so true
So because again, these gas particles are bouncing off of other gas particles. So, and if you can get a flow of gas particles to help push that other gas away, that's a good
That's
thing.
why you open the window.
Yeah. Okay, now, here are the equations that we'll be using for our effusion and diffusion. The nice thing is, they're right on the back of your periodic table. So if you take a look at the back of your periodic table, they're right here on the bottom. So they're right there for you to access. Okay? I'm not trying to hide anything from you. And what this is, and I hope you all have a square root button on your calculator, and we'll do some calculations with this. Well, try to find it again. This first equation, and I'll actually make it a little bigger. Okay? The big M, what does big M represent again that we talked about earlier? Molecular mass or molar mass. Now, this is really important. Listen, guys. Whenever we do molecular masses with this type of setup, it cannot be in grams per mole. That's a no-no. Okay? The molecular mass for this situation must be in kilograms per mole. Okay? The reason why is because the R value that we're using is actually 8.31, and this is on the back of your periodic table. It's in joules per mole Kelvin. Okay? You also have on the back of your periodic table, there's a conversion for what a joule is. 1 joule of energy is a kilogram meter squared per second squared. Okay? You have seen this before?
Wait, yeah.
Oh, cool.
We've done joules before.
Okay. And we did speed of light.
Yeah.
Okay. So that's where you may have seen the meters per second. Okay. So when we use our R, then we have this value here, the 8.31. But what we need to do is we need to convert our joule from joules to kilograms meters squared per second squared. It'll make a lot more sense when we do an example. So the two things, and of course, temperature must be in kelvins since it's a gas. So the molecular mass needs to be in kilograms per mole. The R is this R that we're using, not the atmospheres, because what we're doing is we're looking at speed here, how fast the particle is. Now, before we do any calculations, who do you think is faster? A really light gas or a really heavy gas?
Heavy. One with more training. Heavy.
Yeah.
I hear heavy.
It'll go right.
So which one's faster?
I think it's light.
And we'll assume that they're under the same temperature and the same pressures. Okay. The heavy one? Does everybody agree with that?
No.
Think about it.
I don't know.
Is
I
it,
think light
if
gas.
I were going to run another marathon and say I ran it against Zach, who's the other runner in here, okay, who do you think would win? And we both had the same amount of training. Zach, he's lighter. Okay? So the lighter the gas particle, the faster it is. Okay?
That's why runners are like this big.
Exactly. Yeah. I didn't run in high school. This is a football body. Okay?
Like
This body should not be running. Trust me. Go ahead.
Like molecular.
That's momentum. That's woo. That's what gravity. Okay. If I'm propelling myself and Zach is propelling himself, Zach's going to win.
I beg to differ.
He should be faster than me if we had the same amount of training because I've got more mass to carry than he does. Okay. Now, what's crazy is when we look at two different gases, whether it's radon, me, or Zach is hydrogen, we both have the same pressure at the same temperature. So that means we hit with the same amount of force. How's that possible?
Science.
Well, you got to remember, I'm bigger, so I'm not moving as fast, but Zach is lighter, but he's moving a lot faster. So when you add up that mass and that speed,
It equals out.
it equals out.
Is that
Exactly.
like a car? Like
Yes. Correct. Yeah, so the bigger car versus, if you're in a little car, you better be moving fast if you want to equal out that crash. Of course, I wouldn't want to be in that car. But,
Like a smart
yeah,
car.
so bigger, no, those are not what you want to be in.
No.
They're safe.
They're smart.
I haven't seen one in an accident yet. But when we look at this type of equation, make sure that we're doing this. Kilograms per mole, and then we'll do joules. So let's take a look at our first example problem.
They do.
I'm not getting this.
I can't even.
Go
fit
get
my
in there.
plug.
All right, and this equation here, guys. This is called the root mean square speed, and you'll see RMS. I'm not real sure what the U represents here. Don't worry about it. The first practice problem at the bottom of page 24 says, what is the root mean square speed for propane gas at room temperature, which is 20 degrees Celsius? So we've got propane, which is C3H8, and we're at 20 degrees. Okay. So we will use, what do we need to do first? We're going to use this equation, so what do we need to do to this? Okay, well, sure, we'll convert to Kelvin, get that out of the way. So 293. So what do we need to do to that? Find the molar mass, good. So 3 times 12.01.
Convert it to kilograms.
And then we will. So 8 times 1.008.
You realize you put your parentheses around the
I know, I'm sorry. Forgive me. So 44.094, and that's grams per mole, but we need to get that to kilograms. So 1,000, what is it? Is that what? So we have 1,000 grams for every kilogram. So the grams cancel out. What's my unit there? Kilograms per mole. All right. So divide that by 1,000.
Wait.
Now we don't want to round this yet because we'll use that. So there's our molar mass. Okay. So, okay. So make sure you can convert that. All right. So now we'll plug it into our equation. So we have 3 RT over big M squared over that. So we'll plug in 3, and I'm gonna show this first, and then I'll convert it. Temperature we said was 293, and the molar mass is 0.44094 kilograms. Whoop, per mole. So mole goes up here. And don't forget, we still have our mole Kelvin on the bottom here.
Where'd you get the?
Okay. All right. So let me explain what I just did here. So the 3 obviously is the 3. The R, here's my R with my mole Kelvin. My T is my temperature. My M is my molar mass, and that's kilograms per mole.
How'd you get the R?
It's right here.
It's always that.
It'll be that for this situation.
Gotcha.
Okay. Now, this is one reason why we need to change the joules into kilograms meters squared per second squared. Because as I look at my units right now, the moles can cancel and the kelvins can cancel, but I'm left with a joule over kilogram. That's not good. Now, if you are efficient because you're limited on your space, you can automatically change the joule right out of the gate there. But I'll always show this, just so you can see where I'm going here. So 8.31 kilograms. You can set it on the desk there, Megan. And so now I'm going to put my meters squared on top and my second squared on the bottom. So now when we look at this, so when we look at these units, we can cancel out kilograms, we can cancel out Kelvin, we can cancel out mole. What unit remains there? Meter squared over second squared, which is a good thing to have, because when we type all this in, and let me do that real quickly here.
Hey, Craig,
Yes.
why is the mole case on the bottom?
The mole K, because it's, again, opposite here.
But if you changed it to
No,
the
no, no.
bottom one, like you get what I'm
No,
saying?
the only thing that changed was kilogram. The joule changed to kilograms to this. The mole Kelvin's still mole Kelvin. Okay, so my R, which is this, the only thing that's changed was this for the joule. The mole Kelvin's
Oh,
still
okay,
in play.
okay.
Yeah.
So like really like you could write that as J equals all that over mole K.
Yeah. Yep. That's perfect. Actually, I got this. 1, 6, 5, 6, 5, 7. I'll stop there. And my units, and I haven't taken the square root of it yet. What are my units right now?
Meter squared per second.
Meters squared per second squared. Now we take the square root of the number and the units. So what will my units be?
Meters per second.
Meters per second, which is a rate or a speed, correct?
Yeah.
So if I take the square root of that, 407, right here?
Yeah.
So 407 meters per second. Now, that's just a little bit faster than I can run. Okay.
Uh-huh.
So gases are moving at a pretty good clip. And that's even propane, the thing that we use to barbecue with. And let me also point out, this is really in a vacuum, where there's no other gas particles colliding with it. Because what's actually happening in reality is, you've got this propane that's colliding with something else and it'll divert the path. So it's not really moving at 407 meters per second in our atmosphere because it's colliding with everything else. It's kind of like, okay, the bells just rang, or actually even better, there's a fire alarm and we're trying to get out the door with everybody else in the building. So we're bouncing off of people, we have to hold up and wait. Unless, if it's, the hallway's empty, you're off. Okay. All right, so that's a fun one. Let's do one more practice problem on page 25. Because what we're doing is we're comparing two gases to each other. And the reality is we are using this equation twice.
Do you remember that? Yeah. And the smiley face thing. Stephanie and I had so much fun with that thing in like 6th grade.
Or Miss Titus.
All right,
In math.
now this equation here is comparing two rates. And this is rate 1 and rate 2, or the molarity of gas 1 over gas 2. The nice thing is, you don't have to worry about how this looks, because a lot of this cancels out to where you're just left to this equation here. Okay? And I have in the notes how I did all that. You don't need to worry about that. Just realize that this is the equation that you're going to focus on.
How
Okay.
did you get opposite?
I know, that's what I hate about multiple division lines. We have 3 division lines here, which stink, right?
Yeah.
Yeah, so it stinks. So the good news is, this is the way our equation looks. And it's on the back of your periodic table. Generally speaking, we want to try to make this the lighter of the two gases, okay? So if you look at two gases and you go, oh, I got hydrogen and radon, try to put the lighter gas here, because it'll make it a little more sense when we work this out.
How do you know which one was lighter?
Look at it. You can look at it, you can do the math beforehand.
Look at what?
The gases. Like, the more masses of it.
Oh,
Yeah.
I was like, I don't have all these.
You have this.
Well, I think that might
House
have.
has it.
Yeah. All right, so practice problem number 1 on page 25 says, if compared under the same conditions, how much faster than chlorine gas does hydrogen effuse through a tiny hole? Okay. So, which one's lighter, hydrogen or chlorine gas? Hydrogen, yeah. We have the rate of our hydrogen gas over the rate of our chlorine gas. What happened? Don't do that.
I have a sinus infection. It's
Oh,
not
lovely.
Infection.
So,
He's the scientist.
now, let me ask you a question, okay? If you're a creature of habit, make the masses in kilograms per mole. However, if you use this equation here, does it matter what the units are?
No,
Why?
because that would be the answer based on what you said.
Because the units will actually cancel out. If I have kilograms per mole over kilograms per mole, the units go away. Okay, so just easier to leave it as the molar masses, as we see on the periodic table.
Okay.
Okay, so chlorine is grams per mole. What is he doing back there? You all right?
He's lost his mind.
Is this like easy?
Yeah. So,
Like, can I see it? She's like, see.
so that is, and again, I'm just showing a lot more work than needs to be done, but I want to be able to do that. So we get this. Okay. This is what this is meaning. Hydrogen is 5.93 times faster than
So
chlorine.
you don't even have any.
There's no unit because they canceled out.
Because like the unit would be faster than, right? Like
Do
if
what?
it's-
I don't understand.
Like if, yeah, okay, she gets
The
it.
unit is small.
Wait.
Okay.
I got it.
Now, what do you need to show? Definitely need to show this at least before you show that. Okay.
What if,
So at least plug those in.
what if you just show the 70.9 like you already did?
Then make sure you show the units, because I already canceled the units out on that one. Okay. And the reason why we want to have the lighter gas on top, because it makes more sense. Stating that, yeah, hydrogen is lighter, therefore it should be faster, so it's 5.93 times faster. If you had it inverted, which means that you had these inverted, which means that I would get the inverse of my answer, say that I had these switched, say I had, for whatever reason, I did this, my answer would be 0.1686, or we'll leave it at that, okay? Is that wrong?
No, it's just slower than.
Good, and what this is saying is that chlorine is this many times faster than hydrogen, right? Is that a true statement? Chlorine is this many times faster than hydrogen, which means that it is slower, okay?
What if you accidentally do that? Is it still gonna be wrong?
Can you do
No,
it?
that's what I'm saying, that's why you want to show your work. So if you accidentally put the heavy one on top and you get a value less than 1, then you put
So
the
they're
heavier
both
one.
right.
Yeah, they're both right, but if you say something that's like, okay, faster than hydrogen,
Should you not
Okay.
put slower?
which means that it's slower. No,
Could you put, you could put.
no, because that's a true statement. It's that many times
So it's
faster.
slower, though.
The interpretation is it is slower, but that is a true and accurate statement.
But how slower than not true and accurate? I'm just curious.
I guess. So the homework, the 6, 7s, and 8s,